but his theory proved to be much more important and much more general. And in particular, it allows you to study these very important groups without learning any algebraic geometry. Instead of algebraic geometry, you just use simple graph theoretical geometrical arguments. So I'll begin right away. In order to begin talking about billiards, however, we first need to learn some basic facts about coxeter groups. So for the first 2 or 3 lectures, we'll only concentrate on coxeter groups, and then on Wednesday or Thursday, I will introduce billiards themselves. So a coxeter group is a group together with a distinguished set of generators. And then in order to define a coxeter group, we need first to have a matrix M. So S is a set, a finite set with n elements, and then M is an n by n matrix. It's a symmetric matrix. And each of its entries, so S and T are 2 elements. So this is an n by n matrix, and we'll associate each entry in M with 2 parameters. These 2 parameters come from the set S. And each entry is equal to 1 if it's on the diagonal. And if it's not on the diagonal, it's at least equal to 2, or it's equal to infinity. So these entries are all integers, so positive integers. Or the symbol infinity. When we're given such a matrix, we can associate with it the coxeter group. The coxeter group is the group that's generated by this set S, subject to the relation that the product of 2 elements S and T to the n S T power, this is equal to 1. This is for all elements S and T in the set S. But not for all elements, only those elements such that the corresponding entry in this matrix is different from infinity. This is the definition of a coxeter group. And these coxeter groups will play a big role for us, and they have certain basic properties. So let me make a list of these properties. The first one is, you see, if S is equal to T, then we have here the equation that S times S to the MSS power, but the MSS power is 1. So this relation says that S squared is equal to 1. But in fact, our first observation is that in a coxeter group, the order of every element in big S is exactly equal to 2. And this also says that if we have 2 distinct elements, that their MST power is equal to 1. But in fact, their order is exactly equal to MST. And this is true also if MST is infinity. So if MST is infinity, then there's no relation in the definition. And the order of their product is in fact infinity. Another basic factor, which is not so important, but it will play an important role later on, is the following. If S, suppose S, let J be a subset of the set S, and let T be an element of S. Suppose that T is in the subgroup that's generated by the set J. So this is a subgroup of the coxeter. Suppose that T is contained in this subgroup. And in fact, T is contained in the set J. And the proof of these facts is quite elementary. It involves calculating a representation of the Coxeter group in a real vector space of dimension n. But the arguments that you need to prove these facts are quite different from everything else we will do, so I think it's better just to assume these as axioms. Then we need a definition. First of all, we'll define MS to be the free monoid on that set S. So this is only a fancy word for the set of all words in the alphabet S. And you multiply two words just by putting them together. So in particular, you have the empty word. This is the identity in the free monoid. And if we have a word F, so it's a word, so maybe S, T, U, and then we define its inverse to be the word written backwards. So this is the word. Just wait for me, you know that I have inverse. But this is not a group, so you can't cancel, so there's no inverse in the free monoid. And in the free monoid, there's a particular word that we need to define. So we define, we choose two elements of S distinct. Then we add P, S, comma T. So this is the word that ends in T and then alternates T, S, and so on. And has exactly M, S, T factors. And this is defined only, for those S and T such that MST is finite. So this makes sense. You write as many factors. You can't say what the first letter is. It depends on the parity of MST. So if MST is odd, then it ends in T. If it's even, then it begins in S. So for example, if MST is equal to 3, then PST is equal to TS. And we make the following observation. Suppose we take the word PST and we multiply it with the word PTS inverse. So what do we have? We have this word. It's the word that ends in T and has MST factors. And then we concatenate it, we multiply it with the inverse of this word. So this is the word that ends in S. So when I put the inverse, it begins with S. So we start with S, T, S, T. And again, we have M, S, T factors. But now we see that there's no doubling up. Here this ends with T and this begins with S. So what we have is just the product of S with T, Mij times. This is if Mij is even, and if Mij is odd, we get this product. So for example, if I let MST equal to 3, then what does this product look like? This factor is TST, and this factor is STS. And when I put the inverse, I get the same word. And when I multiply the two, you see I have TS. It's exactly 3 factors of T's. And now there's a natural map that goes from the free monoid to the Coxeter group. So a canonical map that just takes an arbitrary word in MS, and it goes to the Tufts group. Where does it send this word? Well, we'll call the image R sub F. So you just take this word in the alphabet S, and you regard it as a word in the alphabet. Well, when you set a generator of W. But I claim that, and then you regard this word, this product of elements in the generator here as an element in W. So now we need another definition. We have three kinds of transformations. Of elements in the free mono. So the three types look like this. You take a word which starts with a word F, and then you see some element in big S appearing twice in a row, and then some other one. So F and G are arbitrary words. But suppose you have a word that looks like this. So somewhere in the word you have a double letter appearing. And then you just delete this. You delete this double word. This transformation is called a deletion. And then we have a second kind of transformation. You take any word and you divide it into two pieces, F and G. Remember, F and G could be empty, or they could be not empty. If you pick some place in the middle of the word and you insert a double letter. So this is called an expansion. And then we have a third kind of operation. It's called elementary homotopy. So an elementary homotopy is something you do when you see a word that has a PST in the middle. So this is the PST that I defined here. If you have a word, and somewhere in the middle of this word you see the subword PST, then you just substitute PTS. And this is called an elementary homotopy. You'll see why it's called a homotopy in home. And then we say that two words are equivalent. And we write this I'll just say it in reverse. F and G are equivalent if I can start with F and obtain G by a sequence of elementary equivalences. So you see that all of these operations, also notice, all of these operations are invertible. If I do a deletion, I can undo it with an expansion and vice versa. And if I do an elementary homotopy, well, I can just do it with the same elementary homotopy again, and I get back where I started. So these operations are all invertible. And so this is clearly an equivalence relation. So if I can transform F into G by a sequence of deletions, expansions, and elementary homotopies. And our next observation is that if F is equivalent to G, so if we have two words in the three monomers which are equivalent in this sense, then they have the same image in the capsule group. Let's see why this is true. Well, it's obvious for deletions and expansions, because in the capsule group, S times S is equal to the identity. But it's also obvious for this kind for an elementary homotopy because of this observation. So we just proved that the product of MST and MTS inverse is equal to the identity in the capsule group. Both of these elements are the identity in the capsule group. So that tells us that PST and PTS have the same image in the capsule group. So when I do an elementary homotopy, I get two words that have the same image in the capsule group. And so we've had three axioms, two axioms so far. And the third axiom is that these two things are equivalent. And the proof of the first two axioms involves an elementary representation. The proof of this third axiom simply involves thinking about the definition of a group generated, well, a presentation, what a presentation means. It's an elementary argument to show that this is true. I'm not hiding anything deep, but the argument, again, is not so instructive, and so I'll just take this again as an axiom. So we have three axioms about Tufts groups: that the order of each generator is 2, and each of the distinguished generators is 2. The order of a product is exactly what it should be, MSD. And then this second axiom is this little technical axiom that we'll only use once later on, but this axiom will turn out to be greatly important. This is the axiom that will really distinguish Tufts groups from any other group. So let me give a couple of examples. So when we have in order to talk about a Coxeter group, we have to start with the Coxeter matrix, this matrix M, which gives us these entries MST. And the Coxeter matrix is usually represented by a diagram, something called the Coxeter diagram. So an example of a Coxeter diagram is this. So how do I interpret this diagram? The vertices of this diagram are the elements of S. And the labels on these edges tell us what the value of MST is. So here I have three elements, S, T, and U. And this diagram is telling me that MST is equal to 3, and MTU is also equal to 3. And since there's no edge connecting S and U, the convention is this tells us that MSU is equal to 2. So when MSTU is equal to 2, we should emphasize, what does this mean? This means that SU has order 2. But these elements are all elements of order 2. Oops. This product is equal to 1. But these elements are of order 2, so I can rewrite this as, in other words, when the corresponding entry in the matrix is equal to 2, the two generators commute. And commuting generators, well, we just don't put an edge, that's the convention. And if we want to, we can change this to an infinity. So this is an example of a Coxeter diagram, and from a Coxeter diagram you can always reconstruct the Coxeter matrix. And from the Coxeter matrix, we have a unique Coxeter system. The Coxeter system is the pair. So when I talk about a Coxeter system, I mean the pair WS, where S is this, well, W is the Coxeter group, and S is this distinguished pair set of generators that is used in the definition of this system. Let me give a couple of examples. So first, and this number n, this is called the rank of the Coxeter system. So if the rank is 1, then the Coxeter diagram looks like this. So W is generated by one element of order 2, and there's nothing else that can be said. W is simply isomorphic to a group of order 2. In rank 2, we have a Coxeter diagram that looks like this. And so what is W? W is a group that's generated by 2 elements of order 2. And a group that's generated by 2 elements of order 2 is always a dihedral group. And it's a dihedral group whose order is twice n. So W is, as an abstract group, it's a dihedral group of order twice this label. In rank 3, let me just give you a picture of this Coxeter diagram. So this is an elementary fact that the group generated, well, with this presentation is the dihedral group of order 2n. A little bit less elementary, but it's a calculation which I'm not going to include. We can determine that this group, this Coxeter group, is a group of order 48, and it has the following geometric description. We take a cube, and we chop each face of the cube up like this. Imagine each face of the cube is decorated with lines like this. And then we pick one of these triangles. And associated with the lines that border this triangle are three planes of reflection. So this triangle is associated with three reflections. So you imagine the cube embedded in three-dimensional real space. And we have a reflection through the plane that cuts the cube horizontally. We have a reflection through this plane that cuts the cube diagonally like this. And then we have a third plane that cuts the cube also diagonally like this and goes through this line. We have three reflections, and you can convince yourself that these three reflections generate the corresponding Kapsula group. So you can see that products of two of these reflections have the correct order, either 2 or 3 or 4, according to which of the pairs we choose. And it's an elementary exercise to show that these three reflections generate a group which is equal to 48. And it's slightly less elementary, but it's a true fact that this group of order 48 is the Kapsula group that's defined by this presentation. So this is a good example to keep in mind as well.
Is it the symmetric group of the group?
The
symmetric group of the group?
Yeah, I think it's the group of all orthogonal maps of the cube. So these are basic facts about Kapsula groups, and we need to get started. And then in order to say something, well, to develop Tufts' theory of Kapsula groups, we now need to open chapter 2, and we talk about the Cayley graph, which will denote by sigma in our Kapsula system. So we're choosing the Kapsula matrix M. It gives rise to a Kapsula system, WS. And what is this? This is a group together with a distinguished set of generators of, each of the distinguished generators is of order 2. So we can introduce the corresponding Cayley graph. So what is this Cayley graph? It's a graph whose vertex set is simply the set W. And when do we have, so here are two elements of W. When do you connect them with an edge? You connect them with an edge exactly when x inverse y. So this is a product of two elements in this group W. You connect these two elements by an edge exactly when this product, we'll call it S, is an element in a distinguished class of generators. And so in this fashion, we describe a graph. This is called the Cayley graph of the Kapsula system. And in fact, this Cayley graph is not just a graph, it's a graph whose edges, in a natural way, whose edges have colors. We can think of the generators as colors that we use on the edges.
But these graphs can be infinitive.
Can we?
I mean, this one can have infinitive vertices.
That's right. That's right. So we're not making any assumptions about W. W could be a finite group or it could be an infinite group. But it's the valency of this graph is exactly equal to the cardinality of S. So we are always assuming that S is finite. So this assumption we'll always make in these lectures. But you're perfectly right. W, in many interesting cases, W is infinite. We'll have a lot to say also about that. But the valency of this graph is equal to the cardinality of S. Because if we choose an arbitrary vertex and the arbitrary element of S, then there's a unique edge with this color S. And the other end of this edge is equal to X right multiplied by S. product of the inverse of x with xs is equal to x. So for each x, so for each vertex of sigma, and for each generator little s, which now the generators, the elements of little s, I will now often refer to as colors. Because we think of them, it's natural to think of them as colors on the edges of sigma. So for each vertex of sigma and each color, there exists a unique edge at x of color s. Even more, if I can generalize this statement in an obvious way, for each vertex in this graph sigma, and for each word, in the free monoid, there's this unique, now I'll use words that I haven't defined yet, gallery of type F starting at x. So let me define the words that I'm using. A gallery, I simply mean a path. So this is another word for a path in this graph. But in this context, the usual word introduced by Tufts is gallery. So what does a gallery look like? You start at some vertex, and you go up by some edge, and then you use another edge, and then you use another edge. And you're allowed to use the same edge twice. So maybe you go back again, and then you go here. And maybe you go back where you started, and you go back. So you're allowed to use edges more than once, you're allowed to use vertices more than once. This is a gallery. Whenever you have a gallery, well, each edge has a color. So the corresponding word that you get from these colors, that's the type of the gallery. So if I have a gallery that looks like this, its type is the word STU in the free monoid. And so our assertion is that if we're given any vertex and any word, there exists a unique gallery of type F which starts at x. This is simply obvious. You take any vertex and you look at the first letter, that's S. Well, there's a unique edge of color S. And then you start here and you say, well, there's a unique edge of color T, and so on. And at the end of this gallery, is an x times Rf. We just take x, and then this point is x, right, multiplied with s, and then this, this is x. This point will be x, right, multiplied by s. This will be x, s, right, multiplied by t, and so on. And so, in the end, actually, that's not true. This is just f. So this is really, because this is an element, these are elements of W. So you're multiplying in this group W. So at the end, we have x times W. So really, what I've written this slightly incorrectly. This should really be Rs. And then this is RST, and this is RST. Okay, but now, in the context of sigma, we can interpret these elementary operations in a geometric fashion. So these are just algebraic operations, but they look more geometric in this context now. We take a vertex x, and we take a path that ends at a vertex y, and a gallery, and this gallery, its type is, we'll call it F. Now, suppose I think of this word F, and I do an elementary expansion graph. Well, what does that mean? That means I go along, and I come to a certain point, and then I insert S, and I insert S again, and then continue along. So the operation of doing an elementary expansion is just the operation, geometrically speaking, of taking this gallery and at some point inserting an extra edge and then going right back again and continuing the wall. That's what geometrically an expansion looks like. And a deletion looks just the opposite. You have a gallery that has a funny thing like this in it. You just delete this